I think we can start. And I would like to welcome everyone to our webinar today, where we are going to discuss FMEA, FMECA, and FMEDA methodologies with focus on understanding the key differences, and we will also share our experiences. And I would like to start introducing myself and my colleague Neil. My name is Baris Arslan. I work as a principal consultant at ORS Consulting. I have a background in mechanical engineering from Lund University in Sweden, and I have spent my career working on process safety, reliability, and technical risk management area. I typically support our clients in the asset-intensive industries and with focus on the safety critical and complex systems, typically in the energy industry, but also chemicals, petrochemicals, and some other industries. So, Neil, if you would like to introduce yourself.
Sure. Hi everybody, my name's Neil Renton. It's great to see you all today. Thanks for joining. I've got a PhD in reliability as well as an MSc in safety and reliability. I'm a chemical engineer by background. I've worked in a number of industries, downstream, upstream, power, and also rail and other utilities. And I've really focused on how complex systems fail, how they go wrong, and what we can do to try and stop that from happening. So that's my background.
Thank you, Neil. And I will continue with introducing to our agenda and the topics for today. We have divided our webinar into 4 parts. The first part will be the concepts where Neil will explain give an introduction to FMEA, FMECA, and FMEDA with some essentials. Thereafter, I will continue sharing my experiences with some applications and essentials based on 3 examples. The first one will be on the application of FMEA in the functional safety area. The second one will be about how we use FMEA and FMECA in the RAM and reliability-centered maintenance context. And the last part will be the system and integrated FMECAs. Thereafter, Neil, you are going to continue with some examples of the pitfalls and how we can avoid them with some examples and summary. And the last part will be the questions and answers from you. And for today, we would like to have a lot of questions and engagement with you. So whatever the questions you may have and comments, please send it to us and we can publish them and we will take it at the end of our presentation. So I would like to continue with your part, Neil, if you can give us an introduction to the FMEA, FMECA, and FMEDA methodologies.
Thanks, Baris. That is great. Yes, I'm going to begin by having a look at some background, some basic concepts, and I'll start with what is it used for, failure modes and effects analysis. It was developed in the 1940s by the US military around munitions reliability, and at the high level it's about trying to improve the reliability of components and systems and to help identify failure and how that can and what we can do to try and stop that. It's one of the very first structured techniques for analysing systems, and it's used for lots of different reasons today. It's used in general product design and development. It's used when we're trying to develop safety-related systems and products. It's used in test programs to try and develop test programs, again with a view to trying to improve the reliability of the system, and also in reliability-centered maintenance technique and maintenance builds, so trying to identify the tasks, the inspection and maintenance tasks that we're going to do going forward to help improve the reliability and reduce the risk associated with failure. So there's lots of different reasons for using it, and we'll go into them over the course of the presentation this morning. Yeah, next slide. So a little bit of background. I said already it was one of the first systematic techniques for failure analysis and developed in the 1940s by the military, the US military. It's one of the most established and longest used risk assessment methodologies available. The failure modes part of it, the FM part and the abbreviation, is about the ways or modes in which something might fail. And a failure, in inverted commas, can be any error or defect that would prevent the component from delivering its function. The second part, the effects analysis, the effects part, that's about studying the consequences of the failures. So what happens when the component fails, both locally next to the equipment, and then also maybe more globally in terms of its effect on the wider plant or system. The purpose of the FMEA is to take actions to eliminate or try and reduce those failures, starting with the highest priority ones. So we want to try, through this structured technique, we want to actually do things that are going to improve the reliability. And one action, some of the actions that sometimes come out of FMEAs are add redundancy or try to remove and design out completely an issue so that that failure can't occur. And we need some way of prioritising that, because complex plants can have tens and tens of thousands of components. So we need to have a way of prioritising it. And we do that using the consequences associated with the failure, and how easy, on whether they can be detected or not, or whether they're unrevealed. Yeah. So FMEA, FMECA, FMEDA, there's a few different abbreviations and a few different terms used. The original approach, failure modes and effects analysis, I've just described. By adding in criticality analysis, the term extends to be called FMECA, so that the C stands for criticality. And then there's also FMEDA, FMEDA, and that involves the diagnostics part. And that was initially developed for electronic devices, but nowadays it's also used for electromechanical devices. And that's typically associated with functional safety work with regards to the derived failure rates. So some small changes and slight changes in tailoring there. The methodology, though, just to give us some context of where those changes fit into the overall methodology. This sort of flowchart explains it a little easier than bullets. It begins on the left-hand side there at planning, which is a critical part of any FMEA, and I'll go into that in a little bit more detail in the next couple of slides. But that planning and that framing the FMEA, what is its purpose, what are the objectives, what are we trying to achieve here, what are we interested in, that is very important when you're trying to set up an FMEA or a FMECA or FMEDA. Once we actually begin the process inside the red box, the first thing we're interested in is identifying what failure modes. So does the valve fail to close? Does it fail to open? Does it provide isolation as examples of failure modes? What is the cause of the valve failing to open? Is it wear? Is it corrosion? So the causes are about the things that are preventing the component or system from delivering its function. Is it fatigue and fracture? Other examples of failure causes. Then on to the consequence part, so the effects part. What are the local and final effects? So locally, what happens to the equipment? Obviously, the valve doesn't open. What are the final effects? Okay, could we get overpressurization? Are we allowing high pressure fluids to pass and go into a part of the system that's a lower design pressure? And trying to understand a bit wider what is the effect on the system if the failure occurs. Can we detect it? How would we know it had happened? And then I'll just keep going along to the right hand side. Do we need to take any action? So is there something we need to improve? Is there something we can add? Is there a task we can take to try and prevent it from happening? Can we grease something? Can we inspect somehow, etc.? Comes out the actions. The little side box down below this on the severity and the likelihood, that's the criticality part, the severity and the likelihood. So what is the severity in terms of consequences? Those could be safety related, they could be commercial, they could be environmental, and the degrade, or they could be more qualitatively defined, just in terms of, you know, catastrophic down to minor. The likelihood, on the other hand, that's obviously about you know, the frequency, and trying to get some sense of, you know, is this a 1 in 10,000 event? Is it a 1 in 100,000 event? Is it a 1 in 10 event? We're trying to get a sense of how often that happens. And the online diagnostic part in the DA just above there, again, would bring that in when we were looking at this after we'd finished on the detection part. So that just hopefully gives a sense of the overall flow of the process. Failure mode, then cause, final and local effects. Can it be detected? Do we need to take any action? And with the sort of tailored part. Yeah, and this gives a sense. I've broken that down a little more detail there. Thanks, Maris. Yeah, you can move on to that next slide. That's great. You know, I've broken that down into a little bit more detail just on valves, the examples of failure modes for valves: fails to open, fails to close. For pumps, that could be failed to start, or stops, breaks down during normal operation. For sensors, it could be no output or fails to function. Those are the types of, that's how we frame the failure modes. The causes of those failure modes, the middle bracket there, you know, it's wear and tear, degradation, external impact, corrosion, leakage of instrument, short or open circuit. And, you know, there's a huge number of these. These are just examples. The team's got to talk about, okay, what can prevent the valve from failing to open? It may be a specific component, and if so, how is that component degraded? And then thirdly, on the criticality assessment, like I've said, so we've got severity and likelihood, and there's a lot of different scales can be used for this, from catastrophic to minor, as I said, and then from likelihood, again, that can be defined qualitatively, or some companies have got some of those things, they've got numbers behind some of those things to try and help the team put these things in order, because as I say, we could have tens of thousands of these in a complex, large system. So the team needs some way of being able to focus their effort. Good. Yes, thanks, Matt. Let's move on. So, tailoring the FMEA. I said at the start that in that planning part of the process, this is of critical importance for the success of any FMEA. The team that are hoping to use the technique need to first be clear about what question there is they're trying to answer. So confirming the purpose and the objectives, that has to be done up front. Why are we doing it? What are we hoping to get out of this? And do we need the criticality analysis to help us rank things? And that, if that's skipped or not framed well, we're going to get into trouble when we actually start to apply it to the system itself. Secondly, then, we'll determine whether we're going to take a top-down or a bottom-up approach. Top-down is typically used early in the design process, where we don't yet have the component list, and we know what the functional requirement is maybe, but we don't yet know how we're going to achieve it. We might look top-down that way, but once we're further into the process, or it's an existing system, we've got the full component list, then typically we take the bottom-up approach, where we start with the components and work our way up in the effects of the system above that. Thirdly, in terms of tailoring the FMEA, we've got to decide at what level we're going to do it. We need to subdivide for complex systems into functional blocks. The hardware items can be divided into smaller, less complex ones, or right down to components and parts. The processes in terms of a sequence of activities or tasks, so we could look at in a stepwise way, and or from a software perspective, instead of hardware, we'd break that down into modules or executable code functions. So this is something that we spend a lot of time on the FMEAs that we get involved in, is trying to get some sense before the workshop even starts. It's critical that we get this idea of Is it hardware, software, or process we're looking at? Is it top level or low level? And just on hardware there, you can get a sense on the assembly for top level, for mid-level sub-assembly, and for low-level component. And as I said, for component, once we know the components, we tend to use that bottom-up approach. So that's helping to frame how the FMEA is actually going to work. So that tailoring part is part of planning, and it's critical to the success of the assessment. We can move on. So I guess in the context of that, when to use it and when not to use it. Well, on the left-hand side, in the yellow there, absolutely, if you're looking at product or component development, all within this high-level idea that we're trying to improve the reliability of the system and manage the risk associated with failure. So we're trying to improve the components and the assembly, and finally the process itself in terms of its overall reliability. And you know, qualification assessments also very important to use at the end to get some sense of what the failures can be, again with a view to ensuring we're managing the reliability of the system. So absolutely you should use it for that. Not so good on the right hand side if we try to apply it where the hazard scenario is not related to component failure. So it's not, something's not broken or failed, but we could still have a hazard present, and that, so a HAZOP or hazard would be more appropriate for that. Also suboptimum if we're trying to determine the actual required integrity or reliability targets. The FMEA can't do that. The FMEA can't help you in terms of the reliability targets. So how reliable should the component be? That isn't the job of the FMEA. It's to help you identify how it fails, but not what level of performance it should be capable of delivering. That's up to you. And there's other techniques for that. It's also suboptimal for where it's a predominantly operational risk or safety review, or more general HSE related assessments. Again, there are other ways to do that. The FMEA is very much focused on improving the overall reliability of the system through getting a better understanding of how the components fail. Yes, that's fine. On to the next one.
Thank you very much.
Yeah, I've reached that, but I hope that's given everybody some sense of at least the background. It's a very old technique. It was used by NASA very successfully in the Apollo missions. It's gone on to be used by the commercial airline industry, the automobile industry, and lots of other industries to help improve reliability of systems. And Baris is now going to take us through some examples that we've been involved with over the last few years to try and show, okay, how does it really work? How is it used? So back to you, Baris.
Thank you very much, Neil. And I have prepared a couple of examples here in different areas. And then these have typically risk and safety focus, which is our core business at ORS Consulting. The first example I would like to touch, it is from the functional safety world. Just the short introduction to what we talk about when we say safety instrumented functions. Basically, we are talking about safety instrumented systems, which typically consist of a sensor, logic solver, and a final element, and they are typically used to reduce the risk in complex safety critical systems, to take the systems to safe state. And these kind of things are well established and outlined in what we say IEC standards 61508 and 61511 for the process industries. So one part of the standards relate to kind of demonstrating that the components, what we call safe subcomponents. For instance, it could be a transmitter, a relay, it could be a logic solver, a programmable logic solver, that the supplier of the components must prove that the components are reliable and it can be used in the safety instrumented systems. And how do they do it? Again, this is also well established in the IEC standards. There are many things, you know, they have to prove that, and they typically go to two paths. Like for the existing components, we could talk about the prior justification that either the asset owners or the system integrators will prove that the components are suitable for the functions. But for the new components, and also this, if you see it from the supplier's perspective, they will need to conduct FMEDAs. And then FMEDA is basically developed in the 80s, and it's, as Neil explained, it's a variation of FMEA, where we also have the diagnostics part to determine and quantify the failures for each mode. And we also include this automatic diagnostic part and typically understand different type of failure modes like fail-safe, detected, undetected, and dangerous detected, and dangerous undetected, etc. And as a result, we can also establish what we call safe failure fraction. So those kind of information, like detailed information, these are required by the IEC standards. And that makes the FMEDA a very suitable tool to drive this kind of components. But is it everything? No. I mean, FMEDA gives you a certain information about those things, but thereafter the supplier of the component may choose to opt for a certificate, what we call a seal certificate, right? And there are tons of other things which must be covered by the seal certificates. A couple of examples here from Rainland, it could be Exida, etc. And they can also put together a certificate which claims that, which actually shows that this product can be used with a given safety integrity level in a function. So as a part of these certificates, the supplier of the certificates do also elaborate on the useful lifetime, because as you may agree, these electric and mechanical components, they have certain useful lifetime where these failure rates are also valid. So if they go beyond the useful lifetime, it means that the failure rate will progressively increase and it will not make them suitable any longer for the intended function. So when we talk about, this is the FMEA part of it, and I think that this has been very useful for the functional safety practitioners, especially in the last 15, 20 years. And this is just an example of FMEA. It resembles actually most of the things here. These are very similar to FMECA, with the exception of the failure rate classification and some failure modes and rates related to automatic diagnostic part. But ultimately, it will give us the required information. So this application is very common for the functional safety related context. And what else do we use the FMECA for? So FMECA and FMEA, they are typically also used for the RAM analysis, the part of the RAM analysis, which stands for reliability, availability, and maintainability analysis, but also reliability-centered maintenance. Again, I would like to refer to your slide about this tailoring part, because it is very important here. Imagine that some of our clients, they develop large complex facilities, safety critical facilities, right? And then as a part of it, at one point during the detailed design, they will have to understand very clearly what components are, what systems are safety critical, and what systems are production critical, etc. And that is typically understood by a high level FMECAs at the system level. And when we go to like one level down, we will need to understand in those systems what components are critical, right? If it is production critical and safety critical. And further on, for the critical components, we need to understand what parts and what failure modes are critical. And in which sense, is it safety critical, production critical, or can it just let it run to fail, so to say? And then why is it important? Because these asset operators must understand and prioritize their resources, right, for the what we call the maintenance build purposes, and also in order to meet the uptime availability targets, they will have to prepare the test procedures. First of all, they will have to select proper components, right, with the given reliability and elimination of the failure modes. Thereafter, they will also need to develop the test procedures, also proof test procedures, and they will need to select the proper test tools, and also they will need to develop their maintenance programs. So this could happen that some systems or components will be subject to preventive corrective maintenance, and some other systems will just be sort of like run to fail type of systems or components. So it is extremely important to use the tailoring part with the top level, mid-level and the low-level sort of like bottom-up approaches to customize the FMECA methodologies so that the asset owners can optimize the plant design and the operating procedures, and it will have an implication, significant implication for the CapEx part of it, and also operational costs with the OpEx part of it. That was my second example. And lastly, I would like to give an example from the integrated system FMECAs. And these are typically used for systems which are complex, and it consists of subsystems. So like, how does it work? Typically, sometimes we face with the applications where, let's say that there are 10, 15 systems. Each system is system critical and safety critical, so that they have their individual FMEAs or FMECAs, but also at one point they will have to interact. And what we say, these are the kind of interfaces and handshakes that there are additional risk drivers and criticality drivers which occurs when the systems have the handshakes. It is like, you could say, like it is like a metro station or a similar thing where we need to understand the failure modes which occur from this interaction. And it really takes an expert approach, because we will have to understand what happens in the interfaces and what kind of automatic system and the control plans exist for each system. So basically, this takes a certain customization. So what we typically do is that for this kind of integrated or collaborating systems, we sit down together with an expert group with our clients and customize the existing FMECA methodologies so that we can detect all the failure modes and reveal a certain type of dangerous failure combinations. So this is the example which I had from the integrated system FMECAs. And I would like to suggest that you continue with part 3.
Yes, Baris, that's great. Thanks. Just go back one slide, Baris. Just go back to that before I go on to this. That, you know, there's a lot of key things Baris mentioned there. Like, you can see that the FMEA or the FMECA can form the basis of such critical decision support. It's helping the team identify what are the important components, which component failures are production critical, which ones are safety critical, what should we do about it. So it's given a deep insight into both the components and which ones are important, and also at that system example, you know, how a complex system can go bad, and what critically we need to do about it, which things are important. And this is, yeah, this is at the heart of it. Anyway, let's move on to some pitfalls. So yeah, Baris and I have been involved in a lot of these. I mean, I've seen them go great, and I've also seen them go terribly. And first, like I said, I stressed, and I'll stress it again, purpose and objectives are unknown. These are some of the things that go wrong. You know, lack of planning, lack of clarity as to what you're trying to achieve with the FMEA. The team composition, needs a multidisciplinary approach, and the team is critical. If you don't have the right people there, the results from the FMEA or FMECA or FMEDA, they'll be incomplete or misleading. An example that I'll give with that, like this first bullet, experienced operators who understand how components degrade. If you've got sort of engineering professionals who are more office-based and you know, more used to design type environments, they don't always have a good appreciation of how real components degrade over many, like, decades. So whether, even if you're doing it, even if it's a design-based FMEA, somebody from operations needs to be there to give an insight into how the components really behave in real life. So that's really important. Also, end users, again, they've got a different experience base from the design team. It mightn't be a maintenance or inspection professional. It might be someone who works in a control room, or someone who's at least someone who's using the component or system. They'll have a really good sense also of where things can go bad. So getting the team composition is of critical importance, and if you get that wrong, yeah, the FMEA is not going to be worth much. Mixing up root causes and failure modes the term failure modes in English, I think people interpret as they immediately intuitively jump to something breaking, and so start listing off the components, or the, you know, it's wear, it's corrosion, and getting a bit of mix up between the failure mode, which is the valve fails to close as it should, and the cause of that, which is wear or corrosion or fatigue or fracture of a specific component. But that's up to the chair and the team to try and keep themselves right on that. Yeah, not tailoring the methodology to the right context. That's back to number one on the planning and objectives. You know, we've got to get the context right, and we've got to be doing the FMEA at the right level if we're going to get success from it. Yep. Move on to the next slide. If we don't subdivide items or processes, or there's misalignment with the objectives, each of the item or process needs to be evaluated. Can this failure mode occur within the product? Would this effect occur? Is the correct root cause? Is this the correct root cause? Are the controls applicable? And that needs to be done to the right level of detail to answer the question you're trying to answer. If you don't go deep enough, you're not going to get to the bottom of it. Number 6, lack of understanding of the interfacing systems and systems boundaries. If you don't get those interfaces, like Barry showed that example there of the London Underground map, or, you know, if you don't get the interfaces between systems or the system boundary itself right, then we might miss critical failure modes, and that would obviously be a bad thing. Making an assumption on prevention detection controls are better than they are. I've seen this happen so many times in workshops where someone says, "Oh, don't worry about that. We've got this widget and it'll identify when something's going wrong, or we inspect that every year and, you know, we'll pick that up." Okay. Then otherwise nothing would break, but somehow it does. So I think there needs to be a realistic, you know, approach to looking at controls. They themselves are not infallible, and so you've got to take your care with that. The last couple, before we move on to the Q&A, yeah, if the FMEA doesn't set it, you can't set the requirements for the system. I said this already. Trying to understand what the target reliability of the system, the FMEA cannot help with that. It can identify which components can fail and what happens when they fail, but as to what level of reliability it should achieve, no, we need a different technique for that, like LOPA, for example, in functional safety. And there's other techniques for other engineering areas. It'll help prioritise, but it doesn't correct. I was involved in one recently that's got a lot of tough problems in it. It's in a difficult system to manage. It's a flare system, actually. And they've got a lot of, the flare system needs to remain online at all times, but they need to do something with some valves that are in it. And the FMEA did its job. It correctly prioritised everything, but it doesn't get round to key issues. It can't help us with that. We can take actions and do stuff, but the FMEA itself doesn't help with what needs to be done. And then finally, and this is, you know, something for projects and people with existing assets to think about, sort of failing to update the FMEA when there's changes to the system can cause problems, particularly where management of change isn't very well controlled. We introduce, you know, put a new gearbox on, a new type of gearbox into a system that's got completely different, maybe a completely different type of gearbox with totally different failure modes. But meanwhile, our maintenance routines have been set up based on the original FMEA, and we've now got tasks and stuff that we're trying to do that just aren't relevant anymore, and we're missing tasks that we should be doing. So yeah, it's important to keep it up to date as you go on. So yeah, few things to think about there as to how things can go wrong with it. And we'll maybe move on now to some of the questions, and hopefully some answers.
I see the questions here, Neil, and I would like to pick up some of those. Well, I think you already answered one of them, which is related to the management of change procedures. Is there a plan? Is the planning a part of any project or management of change procedures? My experience is that sometimes, especially for kind of like startup type of companies, if you compare them with vertical and integrated like larger companies, they do not have all the procedures in place. For instance, the management of change procedures. And I see that they fail to kind of exercise the change control on their system design with significant consequences. At the end, they could have developed a product which doesn't meet the technology qualification requirements, certification requirements, or it could also end up in lawsuits and claims. So it could have detrimental effects on the company. So this is a very good point.
Yeah.
Another part, and you also touched that point already, Neil. And there's another question about what is the contribution of the proof test interval to this proof test to this methodology? I would like to mention that proof test comes into play in two parts. One of them, as I explained, in the functional safety context, where actually when they do the certification and so on, and the supplier can also propose a proof test for the component, but it will also ultimately be validated by the system integrator because it must also fit into their asset management procedures. But proof test interval and maintenance interval will also be an important part of the reliability-centered maintenance aspects for the company to optimize the operational aspects of the plant. On that one, there is one more question. It says, in the context of asset management, what are the main differences between FMECA and RCM studies, and when should which method be used? I would like to suggest that you should see the RCM part, like risk-based maintenance and reliability-centered maintenance, as in like an umbrella, for different sets of studies, if you like. It's a portfolio of studies and efforts, collective efforts, where FMECA could come into in three parts. One of them is high level, the highest level, where you do the top-down approach. And then if you go further down, it will be the bottom-up approach when you have more details about the components and the parts. And so there is a certain, so basically they are not like methodologies which will replace one each other, but FMECA could be seen as one of the portfolio studies in the context of the RCM. There is another question about, okay, so there is another question about after updating the frequency of the FMECAs, if it will be 2 years, 5 years, and 10 years. Here is the thing, like FMEAs and FMECAs, they are typically done by the suppliers, equipment suppliers. They are the manufacturing type of people. They don't have the same procedures to update these kind of things. Reference to my talk about the management of change systems. So there is not really frequency if it is 2 years or 5 years. I would like to refer once again to the change control and management of change procedures. As soon as there's a version change, component change, system change, FMECA must be updated. And that is the answer for this question. So basically,
one thing there, Baris, yeah, like you and I were talking about just how a lot of companies have a detailed internal guideline for something like a HAZOP or a HAZID, and there's usually a lot of detail there as to the team makeup, how often it should be, when it's appropriate to undertake it, or a ReHAZOP, if you like. We don't sort of see the same. There's not the same sorts of documents for FMEAs typically inside asset owners. For very big organisations, there is, but not always, I don't think. And so, yeah, that is something for people to think about. Even a basic one would be helpful, I think, aligned with the international standard.
Absolutely, and then there is a question here. It is you can also answer that. What is the main difference between the FMEA, FMECA, or a HAZOP? If there's a short version to your answer.
Yeah, just I guess very briefly, the FMEA is looking at component failure and how that component, how the failure occurs by corrosion or wear or something else, and then on the effects bit, it's like the valve fails catastrophically, and we might get a loss of containment or something like that. So it's component focused, The HAZOP, on the other hand, that's a structured way of looking at how process variables can change and go out with their design conditions and which components cause that. So we're coming at it from a different angle with HAZOP. We're looking at the process variables in terms of level, pressure, temperature, and flow, and we're trying to understand, okay, which assemblies, which valves, which vessels, which solids can cause those deviations in the variables in the performance of the process itself. So it's coming at it from they're coming at it from two different angles.
There is another question about the useful lifetime. Could you update about the basis and assumptions for the useful lifetime, and if lessons learned for the technical updates are based on when making the building blocks? With regards to, useful lifetime, I want to hear your experience, Neil, as well. But my experience is that it is the elephant in the room, basically. What happens is that these components go out from the warehouses. Some of them are very critical components. They are installed and they are in operation, but they are only valid. The assumptions are only valid for a certain useful lifetime. And for mechanical components, to give you an example, it could be like 10 years and less. But there are many critical components in operation for 20, 30 years where the system owners turn a blind eye and they do kind of neglect the effects of it if there is any undesired incident. What is your experience, Neil?
Yes, exactly, Baris. I think it's very similar. I think there's a lot of that the FMEA can provide a great basis, and the team had some assumptions about the useful lifetime of the component there, maybe using the bathtub curve or something like that. But as time goes on, of course, things do change, and the whole premise of that safety critical assembly, is that the components are operating inside their useful lifetime and haven't started climbing up, the back end of the bathtub curve. And exactly, this gets missed, and this is how things go bad.
So one more important question, and could you also elaborate when and where the function of the component assembly comes into reveal? The effect consequence of a failure mode may be very different based on which functional component assembly shall perform. For instance, raising, lowering the landing wheels on an airplane. It's a very broad and complex but equally important question. What I would like to say is that if you have, it depends on where you are in the development process, right? If you're in the very beginning at the functional level where you develop a critical product, you only know the function. So basically, if you want to do anything, I think you should do something, and that must be based on the function. If you don't even know the function, it means that you only have a very high level concept. So I don't think you are at an FMEA point. But further down, along with the execution, like development progress, I think your FMEA plan, this is what Neil mentioned in the beginning, don't underestimate the importance of the plan. Make your plan and be on the top of your game. This plan must correspond to your development and certification process, if there is any. So at one point of time, you need to go to the bottom up approach, so to say. And if you are at that level with the components and the parts, you don't really need to care about the function because it will be derived from the component and part failures. That will be my answer. And a question to you, Neil. Regarding the team participation and understanding that the end user has all the data and the design, team will always argue in terms of saving costs, etc. Who wins but wouldn't safety play a vital role in the production? So it's about risk ranking, like team composition and so on. What is your take on it, if you get the question?
Yeah, just again, it's a constant course of frustration. It happened in that last FMEA as well. It's a source of frustration that manufacturers, end users have a lot of data in terms of real life performance after it leaves the shop. But manufacturers have a better understanding of the components and the sort of reliability of the components that they've incorporated into their design. Both people are needed to do a good job of the FMEA, but it's very difficult, I think, to get both groups to communicate with each other. I think we need better ways of better communication between end users and manufacturers, but I don't know what the answer to that is because I've been doing that for 30 years and it's not to get any better.
Absolutely. And I think there's another question about, like, if you can elaborate a little bit more on the objectives and the purpose of the FMEA and FMECA and FMEDA. I think it is again it's a very broad application area here. The context is the context you are looking for, indeed, and where you are in your development process and who does it. Like, is it the supplier, a developer of a product, or is it the system integrator or asset owner who tries to demonstrate a certain compliance issues? So I think the context will be like very different from case to case, and it must be developed in the organization on a specific case, basically. And there is one more question, and the question is if you can give some examples of the use of the FMEA for quality assessment or management purposes. Do you have any answers to that, Ian?
Yeah, I mean, I think you can see what we were just talking about, and some of the questions have alluded to this, that we're focusing on components and what failure mode they can contribute to. And of course, on the quality, I mean, that's helping to prioritize the components, and it should help the team identify which components the quality process is critical for and maybe which it's not so important for. So in terms of helping identify the criticality components, then obviously this is a great basis, and it should inform the quality plan, and should, you know, it should inform how much effort's been put into the quality management, because obviously that finally affects the reliability of the component.
Yes, thank you very much. I think we should wrap up our webinar for today. Thank you very much, everyone, for joining us today. And I would like to suggest that you check our LinkedIn to see the link to the webinar, where you can see the presentation and also questions and answers to questions.
Nice to see you all, guys. Thanks for coming and listening, and good luck with everything you're doing.